Hi, one of the main notions in the study of metric curves was that of the metric derivative. Today, we want to get into more details about what this metric derivative precisely is. On the screen, you can see the covers we have already covered, 1 through 5, but it's more than 5 videos. So a good comprehensive coverage of the theory of Lipschitz curves or curves in general of finite length. So please check out those videos if you haven't yet. And also don't forget to subscribe if you are already following the content. That makes some change on my end. Okay, with that out of the way, let's go to a quick recall of what metric derivative was and why it was important. You have a curve that goes from some compact interval into an arbitrary metric space equipped with the distance d. And we say such a curve has metric derivative at t, and we denote it by this notation. It's only a notational thing. There is no such thing as gamma prime, as will be the main point of this video. And it's defined, of course, only using the metric structure. So you compare the distance of gamma t to gamma t plus h, and you take a limit. The significance of this metric derivative notion was that for Lipschitz curves, this derivative exists almost everywhere. And once you integrate it, you recover the length of the curve, which was the variation of gamma defined through partitions of AB. Today, we will talk about a precise description of this derivative through actual componentwise derivatives. Okay, so to talk about genuine derivatives, we need some sort of linear structure, because derivatives require subtracting two values, and that means we need some linear structure. So we are in a vector space, and because we need some sort of convergence, we need a topology, and the best is if it comes from a norm. So we have a normed vector space X, we have a curve that maps into this vector space, then we say it is differentiable in the strongest sense, which is called Fréchet differentiable, as is also used in the calculus. We say it is differentiable, Fréchet differentiable at t, if there is some element in the vector space, which we denote by this, such that this difference quotient converges to that. And the convergence is in the norm, which means we say yn converges to y if their difference norm converges to 0. So these are real numbers, and we know what it means for that to converge to 0. So that's just the definition. The claim is that if you have a curve that is differentiable in this strong sense, then it is differentiable in the previous sense of metric differentiability. So therefore, metric differentiability is a weaker requirement on a curve than Fréchet differentiability. The reason for this, the proof of this, is because if you have a sequence of vectors in a normed vector space that converge to y, then, so in convergence in norm, then the modulus of those vectors converges to the modulus of the limit. So these are vectors in the vector space. These are real numbers, and this implies that, of course, the reverse is not true, even for a vector space as simple as R1, the real line, because the sequence of plus minus ones converges. Their absolute value converge, but of course, plus minus 1 does not converge to anything. Okay, so if we have this better differentiability, then we get metric differentiability, and the metric derivative is exactly the norm of this Fréchet derivative. This is very important because it includes the Rademacher's theorem predictions for metric differentiability. In particular, if you have a Lipschitz curve that goes into a Euclidean space, we know that gamma prime exists. That means the curve is Fréchet differentiable almost everywhere, and therefore it is also metrically differentiable with the metric derivative being the speed of the vector. And we had seen this before, in fact. If you map into some other vector space that is of finite dimension, then basically it's a copy of Rn with some different norm. For example, L infinity norm. And because every two norms are by Lipschitz equivalent, that means there are constants such that one norm is less than or equal to this C, the other norm, and also there is a lower bound with a different C of that. Because of this, if you have Lipschitz curves into this finite dimensional normed vector space, then basically you have Lipschitz curves into Rn. When you forget this new norm and replace it with the usual norm. And then by Rademacher's theorem, it is Fréchet differentiable. That means gamma t plus h minus gamma t over h converges in the Euclidean norm, this is Rademacher's theorem, to some gamma prime of t. But because of this by Lipschitz equivalence of norms, this implies that it converges also in the new norm on Rn. And then from previous observation, their norms, their new norm of this quotient converges to the norm of gamma prime of t. So we have the strongest convergence, and whatever norm you equip your space with it, then you take just norm of this convergence on both sides. If you take L infinity norm, this becomes L infinity norms. So Rademacher's theorem also gives the case that if you have any finite dimensional normed vector space, then Lipschitz curves into those spaces are Fréchet differentiable, hence also metrically differentiable. And I want to give you a concrete example of how this can be applied. Let's say we want to talk about the perimeter of circle if we give R2 the maximum norm, which means the norm of xy is the biggest of x and y. Okay, and we had seen this in some of the videos before. Now we want to compute the length of the circle, which by which we mean the curve gamma t equal cosine of t sine of t, where t is between 0 and 2 pi. So we want to compute the length of this gamma, but in the L infinity norm on the plane. Well, by this theorem we saw in the beginning, this will be integral from 0 to 2 pi of gamma prime of t in the usual sense. But then for the metric derivative, we need to take the norm in that metric, dt. And so gamma prime of t will be the maximum of, well, cosine of t is negative sine of t, but its absolute value is just same as absolute value of sine of t, and cosine of t, the other component, dt. And then by symmetry, this you can see that this is 8 times 0 to pi over 4. where always cosine of t will be the bigger of the two, and also it's positive. And this becomes 4 times root 2. And let me, instead of calculating this, let me jump to also geometrically justifying this. Well, from here to here, I want to show, find the length from here to here. Because we are using the L infinity norm, if you take any 2 points on this curve, their L infinity distance will be just the elevation. It will be the difference of the heights, difference of y values. Because the L infinity norm, you take this thing here, this line, and then you look at this projection and this projection, and whichever is bigger is the distance. And here we see that for this red segment, it will be the case that for any pair of points you take, their distance is equal to the difference of their projection onto y value. So if we write a partition of this curve and we add up the mutual distances, this will simply add up all the differences from this y value 0 starting here all the way to this. So it will be just this length. And if you are at pi over 4 here, this is root 2 over 2. Therefore, the variation in L infinity norm of this segment will be equal to this height difference, which is root 2 over 2. We have by symmetry 8 many of these, and that gives this quantity. So just showing how we can do actual calculations with this theorem, that if you are Fréchet differentiable, your metric speed is just norm of the Fréchet derivative. And this fact that in finite dimensional normed vector spaces, you treat the curve first as if it is into usual Rn, you find its Fréchet derivative, and then you take norm in the new norm. Okay, so here the keyword is finite dimensional. The question then is, do we have similar stuff for infinite dimensions? And unfortunately, the answer is no. We will see a counterexample, and then we will also discuss how close we can get to any sort of differentiability in such generality. But for both of these, we need to introduce some infinite dimensional vector space, and a good one is the space L infinity. This is the space of all bounded sequences. So any sequence of real values with a uniform bound on them. And this space has some obvious linear structure. You know how to add these vectors. Just extend whatever you know from Euclidean. Just do them infinitely many times. And this quantity, because we assume is finite, we can define this to be a norm. Of course, one has to check triangle inequality and a couple things. But these are pretty standard functional analysis or even just analysis stuff taught in many basic courses. There are some properties of this space that we will need. First of all, it is the dual space to L1. So later we will see specifically what this means, even if you don't know what any of these dual space words mean. There is a particular subspace of this L infinity called C0, and it is those sequences that converge to 0. So the tail converges to 0 if you are in C0. If you have a sequence that converges to 0, then it is actually in L infinity because, well, because of this, the tail is bounded and you have only finite initial stuff. So all of them are bounded by some uniform number. The key here is that it is closed. And that is a beautiful exercise to do you need to show that if you have a sequence of sequences, so you have to take x1 in L infinity, x2 in L infinity, which means each one of these x1, x2, and so on is a vector. So you have to show that if these are vectors in C0, such that xn converges in this norm to some x, then this x also belongs to Z0. That means you have to show that this x is also such that its tail converges to 0. So that is the exercise. Another very important thing about this L infinity is that it is so large that every separable metric space has a copy of it inside L infinity. And that copy is exactly a copy because it's an isometry. And a metric space has nothing other than its metrics. So when you isometrically embed it in L infinity, you preserve every single structure on this space. And this is famous Fréchet-Kuratowski embedding theorem. I have a separate video specifically on this with proof, plus some further discussions of it. Okay, so that's one thing that is very important to us here. And then projections onto coordinates are one Lipschitz. So here, by projections, I mean, say x, so pi is a map which goes from L infinity into R, say k, and x1 to infinity maps to, say, a choice of k many of these. So I1 and xik. Maybe you pick the first case, which will be then x1, x2 until xk. But you can also say you pick x1, x3, x5, just the odd ones, k many of them. So any choice of these, even you can have still a countable thing here. The reason for being one Lipschitz is that this supremum will be less than or equal to supremum over a certain subcollection of them. That's just tautology. A curve into L infinity is L Lipschitz if and only if each component is L Lipschitz. These all follow from this particular definition of the norm, that it just takes the biggest of these. And we will see the effect of this being this way in a future example. But the point is, they never add up. It's not like the distance of, say, x to another one, to x prime with coordinates x1 prime, x2 prime, and so on. Their difference, x minus x prime, and then norm, which is just distance of x from x prime, is the biggest difference in some coordinate. And if you find one coordinate which has the largest gap, you don't add that up to other coordinates. So you only pick one of them. So for example, 1, 1, 1, all the way to infinity, and 2, 2, 2, all the way to infinity, their distance is equal to 1, because you get this gap equal to 1, this gap equal to 1, but they don't add up. You look at the biggest one of them, and it's always 1. So that's a big difference between the Euclidean norm we are used to, because you square this gap, you square this gap, you square this gap, you add them up and take root. So whenever you have a new difference in some component, it adds to the distance. But with L infinity, that doesn't happen. It doesn't matter if you have new differences further on. As long as they are smaller than the difference in the first or in the fifth, they don't contribute. The points don't get farther away if they keep being different at the tail. Okay, now that we know our L infinity a little bit, we can give an example of a Lipschitz curve, which is not Fréchet differentiable anywhere. And that is a very compelling counterexample to Rademacher-type theorem. So we saw that Lipschitz curves into finite dimensional vector spaces are in fact differentiable almost everywhere. And this is the exact opposite, that they are. This one is nowhere differentiable, although it is Lipschitz, which means that any hope of a Rademacher theorem in infinite dimension will fail. Now, about the proof of this, okay, here is the nice proof that I have learned from my PhD advisor, Piotr Hajwasz. Well, for every t, gamma t is inside C0, this subset of L infinity of sequences that converge to 0. And because here the numerator is always bounded by 1 and -1, and denominator goes to 0, so every t you pick, this definitely will be a sequence that goes to 0. So for every t, gamma t is a point in C0. So for every h other than 0, gamma t plus h minus gamma t divided by h is also in C0. Because C0 is a linear subspace, subtracting, you remain inside the subspace, dividing by a real number, which is scalar multiplication, you still remain in C0. So if gamma t plus h minus gamma t over h converged in norm, in infinity norm, to some gamma prime of t, then this gamma prime of t would be in C0. We can also look at component-wise. Okay, so here's more. Also, it is easy to see that then, if this quotient converged to some gamma prime of t, then well, let's give this a different name, because if this converges to some say z, a vector in L infinity, that's the definition of Fréchet differentiability, that this quotient converges to some vector in our space. So if these converge to some vector, then this limit would be in C0. Also, it is easy to see that then z would have to actually be the derivative, component-wise derivative, and that is something that needs to be done. But if this quotients converge, then in every component they have to converge. And if you write the quotient for one component, that is just the usual definition of the derivative of a real valued function. So this will give you cosine of t. This will give you cosine of 2t, because every time this 2 and 3 comes out and cancels the denominator, this will be cosine of 3t, and so on. Then z would have to be this. So on the one hand, z is this. On the other hand, z belongs to C0. But for t in 0, 1, z is never in C0. For any fixed t in this range, cosine of it does not converge to 0 as I goes to infinity. Maybe another nice exercise. And that's a contradiction. So if you had strong convergence for this quotient, you'd run into trouble. So this quotient does not converge to a vector. Therefore, there is no way we can have Fréchet derivative by definition. Okay. Remember that we had Fréchet-Kuratowski theorem, which said that if you have any vector, any metric space, then you can embed it into some Banach space. In this case, L infinity. So if metric space is separable, you can have this Banach space to be L infinity. And in fact, if your space is not separable, you can embed it still in a Banach space, but with larger size. But anyway, this shows that Lipschitz curves in from AB into arbitrary metric spaces, they fail this strong differentiability, not because there is no way to define this linear structure on an arbitrary metric space, but because in fact metric spaces are infinite dimensional. In other words, after you embed it into the Banach space, say Y, with a linear structure, you can make sense of this quotient. So it's not about just whether you can write down the quotient or not. The problem of differentiability, the lack of the Rademacher theorem, has to do with infinite dimensions. And it's not simply because we don't have linear structure. Okay, that's our counterexample. Now we want to see, can we do, but on the other hand, we saw that we have metric differentiability almost everywhere. So is there something in between? Can we do a little bit better than just metric differentiability? And the answer to this has been found. Basically, we can characterize those Banach spaces where all Lipschitz curves are almost everywhere Fréchet differentiable. And those are the spaces that are equipped with the property called Radon Nikodym property. There are many different characterizations of, so many equivalent definitions of this. For example, the closest which justifies the naming is that the classical Radon Nikodym theorem holds for x-valued measures. Okay, there's a lot to be unpacked here. That's one definition that I chose here because it justifies the naming. And looking at this, one doesn't see any connection to curves or Lipschitz curves, but it's interesting that it turns out that a space, the Lipschitz curves into this space have the Rademacher theorem if and only if your space has this Radon Nikodym property. And that's just amazing how these get connected, how this becomes an if and only if property, if and only if theorem. Okay, we don't want to talk about this in detail here. So let's move on to this again question of can we do better than metric differentiability? Okay. We already mentioned that L infinity is the dual space of L1. So L1 is again a space of sequences, but this time we require more. We require that they be absolutely convergent, their summation. Okay, and this sum is the L1 norm. The way L infinity is dual of L1 is that objects in L1 act on objects in L infinity act on objects in L1 by the following pairing. And this is just again notation, but it agrees with the way we do dot product in our N. So one has to prove, first of all, that this is a real number. So that means this summation is finite, but that's easy probably from the definitions. So xi's are bounded. You can put the worst there, and then even if you take absolute value of yi's, because of this, they are convergent. Anyway, and you can see that this is bilinear. It's linear both in x and in y. So that is the pairing between L infinity and L1. And the fact that L infinity is the dual space of L1 means that basically all linear maps from L1 to real numbers come from such a description. Okay, then there's the notion of weak star convergence. And that is a sequence of points from L infinity. Okay, a sequence in L infinity, weak star convergence to another value in L infinity if this holds, that the action of xn on y converge to action of x on y for every fixed y in L1. And this, I don't want to discuss what weak convergence is, but weak star convergence is the weakest of all the convergence, maybe. And here is an example illustrating this. If you have this sequence, so this is in L infinity, this is in L infinity, every single one of these guys is in L infinity because their infinity norms are equal to 1, despite having a tail of all ones. And these weak star converge to just 0, 0, 0. The reason being that when xn acts on y, this becomes the summation of x I, y, I, only if, okay, this is by definition in n, but notice that xi's are 0 until point n, and this becomes n to infinity, and then xi's become equal to 1, so this becomes yi. Remember that y is fixed, so this goes to 0 if n goes to infinity. You have a convergent sequence if you instead of adding from 1, you add at a later point, and then you push this later point on and on, the tail, the sum of the tail converges to 0. This becomes equal to the 0 vector acting on y. And here we have that xn dot y converges to 0 dot y, which is exactly this. So the sequence of having tails 1s, but this tail being pushed to the right every time, this sequence converges to the 0 vector in weak star convergence. And if that just doesn't feel right because it's a very weak convergence. One thing about weak convergence that is true in even more generality is that this weak star limit has norm less than the limit infimum of the norm of the sequence. Basically saying that it's smaller than all of them in the tail. Okay, why are we introducing all of this? The thing will be that if we start with a Lipschitz curve into L infinity, and these are the components of that curve. So for every t, gamma t belongs to L infinity, so it's a bunch of real sequence as real numbers, and then we give them just names. So this is just naming. And we have seen before that if the curve is L Lipschitz, in fact, if and only if the curve is L Lipschitz, if and only if each gamma I is L Lipschitz. Therefore, gamma I, notice that gamma I is a vector, is a function from AB into real numbers. And if this is Lipschitz, then it's differentiable almost everywhere. So this one is differentiable almost everywhere. This one is differentiable almost everywhere, and so on. Every time you throw away a null set in AB, outside of which this is differentiable, you throw away another null set outside of which this one is differentiable, and so on. But the good news about null sets is that even if you throw out countably many of them, you still have thrown out only a null set. And therefore, there's a null set you can throw away, and then for every t, all of these are differentiable simultaneously. So for almost every t, you can formulate this vector. And as we saw before, if this gamma t is going to have Fréchet derivative, this is the only candidate. So if gamma is Fréchet differentiable, then gamma prime of t must be this vector here. But then our counterexample showed that this does not have to be the case. Although you can write down this vector, it doesn't mean that the convergence is strong, as was the case with this sign of it over I vector. But the positive news is that under these assumptions, at almost every t, these quotients, although they may not converge in norm, they weak star converge to that vector. So if there is no weak, this means that it's Fréchet differentiable. With this weak star added, it's just that. It's a weaker form of convergence. As we saw in the previous slide, because this is the weak star limit, the norm of this thing is less than or equal to the limit infimum of this. But we have more here. We have that the norms, in fact, converge to that. So there's more than a generic weak star convergence. It's not just a weak star convergence, it's also convergence of the norms. It's not convergence in norms, convergence of the norms. So this tells us a little bit more about differentiability, because this second line is just saying gamma is metrically differentiable at t. This is the definition of metric derivative, because the numerator is just distance of this from that. And not only we know that this converges, so it's metrically differentiable, we also know its value. Its value is equal to this. And the best thing about this is that these are computable quantities, as I will do in the next slide. So if you know your curve into L infinity, and you know its components, then simply take componentwise derivatives, and then take the L infinity norm of that infinite vector. And that is your metric derivative almost everywhere. Okay, the corollary of this is that we can prove this metric differentiability theorem using that. We want to show that if you have a curve, a Lipschitz curve, into an arbitrary metric space, then gamma is metrically differentiable almost everywhere. We want to prove this using previous result. But previous result is about maps into L infinity. So what should we do? The first thing we do is we want to embed x into L infinity. We had the result, the Kuratowski-Frechet embedding theorem, only for separable metric spaces. What if x is not separable, is huge? Then there's no problem, because differentiability only concerns the image of gamma. In the definition of differentiability, metric differentiability, you only compare gamma of t plus h, distance gamma t. So we don't care about the rest of the space. So we can even ignore that. And therefore, the image of the curve is always separable because it's image of a compact set. So we can embed x, or the reduced x, in L infinity isometrically, not changing the distances. Therefore, we can imagine without loss of generality that our curves are actually being mapped into L infinity. So that takes care of that technicality. Then the second part of the previous claim, as I wrote down, is exactly saying that this curve is metrically differentiable. yeah, and then distance gamma t plus h, gamma t is just norm of gamma t plus h minus gamma t, where I'm identifying this isometric image of this with itself in L infinity. Okay, highly non-trivial corollary of the previous description of metric derivative is that if you have a curve in L infinity, then you can recover its length by looking at its finite projections. And for this, I need to draw some pictures. Suppose you have a curve in R3, okay, like this. If you project this curve onto R1, you see some line segment like this. That will be this. Of course, the length of this projection need not be equal to that, especially under this scenario that suppose your curve is like this, and then this segment is just perpendicular to the x coordinate. When you project the curve, all you see is from here to here. And then here, your curve remains constant for the rest of the time. So this length is shorter and strictly so than the length of the actual curve. So the projection misses a big portion of the length. But if you regard this curve in R3, and now if you project it onto R2, then that problem goes away. However, in R3, again, you can create a curve that is, even when projected onto two of the dimensions, misses some of the length. And let me draw one example for that. That example will be just a duplicate of previous one, maybe a bit involved. So what you do is, okay, you have this curve, it bends, but projection onto x and y sees that. But then it goes vertically upward, so that when you project down, this time, this portion is captured, but then from that point on, the curve becomes just constant. This is an overlap, of course. So all of this portion projects to a constant point. Again, you see, you miss some of the length. The L infinity can be viewed as just an infinite dimensionally. So you go, here is R3, you go to R4, R5, and so on. So there are infinitely different perpendicular directions. You can think about it that way. Now, the claim of the corollary is that if you have some curve in this space, ultimately this projections will capture all of the length of that. And with these examples that I gave you, it should convince you that this is not trivial. Because what if this keeps happening, that every time there is some portion of the curve that moves perpendicular to the previous collection of coordinates? So maybe you project it into the first 100 coordinates, but then there is a portion of the curve that goes perpendicular to that, or let's say parallel to the 101st coordinate axis, so that in projection it just becomes constant. So there is no immediate reason why this won't happen. And the theorem says, guarantees that this will not happen. How does this theorem follow from our results? Well, your curve is gamma 1, gamma 2, and so on into L infinity. We have this formula that the length of gamma is integral from a to b of the metric derivative, but we saw that the metric derivative is gamma 1 prime, gamma 2 prime, and so on dt, L infinity norm. But L infinity norm is the supremum of gamma I prime, I belonging to n dt. Now this can be written this way. So you take, instead of supremum, so you can take maximum of these gamma I primes, where I is from 1 to n, so you only do the first n, and then you take limit n goes to infinity. So this is just a different way of writing this. But now, by monotone convergence, you can put the limit outside, and then this becomes a to b, maximum of gamma I prime, I between 1 and n dt. But this is nothing other than the, okay, this one is metric derivative of the curve gamma 1 until gamma n, which goes from AB into Rn equipped with the L infinity norm. Just you truncated it. And this is easy to see because this curve into the finite truncation of this curve is in fact Fréchet differentiable with derivative gamma 1 prime, gamma n prime. Remember the discussion we had about finite dimensional norm spaces, and its metric derivative is just take the norm of this in the appropriate norm, and that equals maximum of these absolute values. So this becomes therefore integral from a to b of the metric derivative of this truncated curve, and that again using the length formula is equal to the length of the curve gamma 1 until gamma n, the projection of the curve or the truncation of the curve. So projection of the curve to Rn is exactly this thing. The limit of its length equals to the limit of gamma, and that's the proof. And I want to finish with this example, which again says that, well, L infinity, although we can think about it as having infinitely many directions, it is not exactly like Rn, because such a thing in Rn, okay, in R1, if you had one coordinate axis, this would be just the curve from here to here, okay, just one direction, 0 and 1. If you are in R2, then here is that curve, T and T. Here's the curve T and T. And this would have length equal to √2, because you have one here and one here. In R3, this is the diagonal like T, T, T. And this time it has √3 because its projection is the previous diagonal. So it's 1, 1, giving √2 here, and then 1 up. So if you do n many, then you get √n, and this goes to infinity. So, but this curve in L infinity actually has length equal to 1. How come? Because all of these computations I did were in the usual Euclidean norm. The difference with the L infinity norm is that if you're in R2, say, for simplicity, this has the same length as this, just because of the way L infinity works. When you look at 2 points, their distance is the larger of the projections they have. And here it doesn't matter actually which projection you take, but the point is you don't add those projections. So going diagonal, going this way, is the same length. That's why if you keep adding new directions, you don't gain new distances. So even the infinite diagonal has only length equal to 1. Now, let's see if our computations guarantee this. So the metric derivative of gamma equals, so you take componentwise derivative, you take usual derivative in each variable, and then you take L infinity norm, and this will be the maximum of these, which is always equal to 1. So the length of the curve, which is integral of the metric derivative, will be, of course, 0 to 1. That will be 1. Okay, yeah, so all works together. So this topic today was a bit advanced and had a lot of concepts to it, but it was also a cool one that I wanted to include. Beginning with my next video, I will switch from the parametric description of curves to some more intrinsic way of even defining the curves. What are some other ways of saying what subsets deserve to be called curves? So until then, have a great one and see you then.